Good morning, everybody. I introduce myself. My name is T.HENSON. I am working as assistant professor in the Department of Mathematics, St. Joseph's College of Arts and Science, Manchakuppam, Kadalur. I am going to teach the subject Ordinary Differential Equations for First MSc Mathematics. Subject code is PMT703. Semester 1. Before I begin the subject, I give the syllabus. Unit 1, Linear Differential Equations of Higher Order. Linear Independence. Equations with the constant coefficients. Equations with the variable coefficients. Unit 2, Linear Differential Equations of Higher Order. Lorentzian. Method of variation of parameters. Method of Laplace transforms. Unit 3, System of linear differential equations. System of first order equations. Existence and uniqueness theorem. Fundamental matrix. Unit 4, System of linear differential equations. Non-homogeneous linear systems. Linear systems with the constant coefficients. Unit 5, Existence and uniqueness of solutions. Lipschitz condition and Grunwald inequality. Successive approximations. Picard's theorem. Fixed point method. Textbook. Contents and treatment as in Ordinary Differential Equations by S.G. Dew, V. Lakshmikantam, and V. Raghavendra. There are 5 reference textbooks. Now I am going to start Unit 1. Linear differential equations of higher order. Linear independent and dependent functions. Now I am going to give the definition. Functions x1 of t and x2 of t are linearly independent on the interval I if c1 into x1 of t plus c2 into x2 of t equal to 0, where t is a point in the interval I. So this implies c1 equal to 0 and c2 equal to 0. Here c1 and c2 are necessarily both 0. Two real or complex valued functions x1 of t and x2 of t defined in an interval I are said to be linearly dependent if there exist two constants c1 and c2, at least one of them not 0, such that x1 c1 into x1 of t plus c2 into x2 of t equal to 0. So based on the definition of linearly independent and dependent, now we are going to do some problems. Problem number 1, prove that the functions sin t, cos t defined in the interval minus infinity to plus infinity are linearly independent. Now we write the solution. Now we take the given functions as x1 of t and x2 of t. So x1 of t equal to sin t, x2 of t equal to cos t. Now we take the linear combination. Let c1 into x1 of t plus c2 into x2 of t equal to 0. Now we can substitute the values for x1 and x2. This implies c1 into sin t plus c2 into cos t equal to 0. This can be taken as equation number 1. So in this linear combination, there are two functions. So we can differentiate the linear combination with respect to t at most one time. So if there are three functions in the linear combination, we can differentiate two times. If there are four functions in the linear combination, we can differentiate three times. Right. Now we are going to differentiate the equation 1 with respect to t. We get as C1 into cos t minus C2 into sin t equal to 0. This can be taken as equation number 2. So our aim is to prove the constant C1 and C2 are 0. So for that, we are going to solve the equations 1 and 2. So equation 1 is to be multiplied by cos t minus equation 2 is to be multiplied by sin t. Then we get this result. In this, this expressions get cancelled. The remaining terms here we get C2 into sin square t plus cos square t equal to 0. This implies C into 1 equal to 0. This implies C2 equal to 0. Substituting the C2 value in equation number 1, we get C1 into sin t plus 0 into cos t equal to 0. This implies C1 into sin t equal to 0. Therefore, C1 equal to 0 plus C1 equal to 0 and C2 equal to 0. Therefore, the given functions are linearly independent. Now we can do the second problem. Prove that the functions e power I into alpha t, comma sin alpha t, comma cos alpha t are linearly dependent. Now we write the solution. We take the three functions as x1 of t, x2 of t, and x3 of t. Now we take the linear combination. That is C1 into x1 of t plus C2 into x2 of t plus C3 into x3 of t equal to 0. Now we can substitute the values of x1, x2, x3. This implies C1 into e power I alpha t plus C2 into sin alpha t plus C3 into cos alpha t equal to 0. We can take this as equation number 1. We know that e power I alpha t equal to cos alpha t plus I sin alpha t. This is a formula. So from this formula we can write this result, that is e power I alpha t minus cos alpha t minus I sin alpha t equal to 0. Here this can be written as e power I alpha t minus I sin alpha t minus cos alpha t equal to 0. We can take this as equation number 2. We compare equation 2 with 1. We get C1 equal to 1 and C2 equal to minus I and C3 equal to minus 1. Here we see that all the constant values are not 0. Therefore, we say that the given functions are linearly dependent. Next problem. Prove that the functions 1, 1 plus cos 2t, sin square t are linearly dependent. Now we write the solution. So we take the three functions as x1 of t, x2 of t, and x3 of t. Now we take the linear combination. That is C1 into x1 of t plus C2 into x2 of t plus C3 into x3 of t equal to 0. Now we can substitute the values of x1, x2, x3. So we get this result. Here sin square t can be written as 1 minus cos 2t by 2. So this is the formula for sin square t. Here, if we take C1 equal to 1, C2 equal to minus 1 by 2, and C3 equal to minus 1. If you substitute these values in equation number 1, then the linear combination will be satisfied. Here we get if you substitute values, we get linear combination gives 0. Therefore, the constant values are not 0. Therefore, the given functions are linearly dependent. Right, next problem, problem number 4. Prove that the functions t square and t into modulus of t defined in the interval minus infinity to plus infinity are linearly independent. Now we write the solution. First, you take the given functions as x1 of t and x2 of t. So x1 of t equal to t square, x2 of t equal to t into modulus of t. The modulus of t can be written like this. That is modulus of t equal to t if t is greater than 0. Modulus of t equal to minus t if t is less than 0. So this concept is applied here. So here this implies c1 into t square plus c2 into t into modulus of t equal to 0. This implies c1 into t square plus c2 into t into t equal to 0 if t is greater than 0. Here modulus of t equal to t if t is greater than 0. So we have applied this one option. So we can take this as equation number 1, that is c1 into t square plus c2 into t square equal to 0. Now we take the other option. This is c1 into t square plus c2 into t. Modulus of t is minus t equal to 0 if t is less than 0. When you simplify this, we get c1 into t square minus c2 into t square equal to 0. This can be taken as equation number 2. So adding equations 1 and 2, plus c2 into t square minus c2 into t square get cancelled. So here we get a 2 into c1 into t square equal to 0. This implies c1 equal to 0. Using this result in equation number 1, we get a c2 equal to 0. Therefore, all the constant values are 0. Therefore, the given functions are linearly independent. Next problem. Verify that functions e power x, cos x, sin x are linearly independent on a real line. Now we write the solution. First, you take the given functions as x1 of t, x2 of t, and x3 of t. So they are e power x, cos x, sin x. Now we take the linear combination. Let it c1 into x1 of t plus c2 into x2 of t plus c3 into x3 of t equals 0. Now we can substitute the values x1, x2, x3 in this linear combination. We get a c1 into e power x plus c2 into cos x plus c3 into sin x equals 0. This is equation number 1. So in this linear combination, there are 3 functions. Therefore, we can differentiate this linear combination with respect to x 2 times. Now we are going to differentiate this first time. So differentiating 1 with respect to x, c1 into e power x minus c2 into sin x plus c3 into cos x equals 0. We can take this as equation number 2. Again, differentiate with respect to x, we get a c1 into e power x minus c2 into cos x minus c3 into sin x equal to 0. This is equation number 3. Our aim is to prove all the constant values are 0. C1 and C2, C3 are 0. So for that, now we are going to solve the 3 equations 1, 2, 3. Adding equations 1 and 3, we get this result. In this result, 2 terms get cancelled. Here we have 2 into c1 into e power x equal to 0. This implies c1 equal to 0. So you substitute this value in equation 2 and 3. So 2 and 3 becomes minus c2 into sin x plus c3 into cos x equal to 0. This can be taken as equation number 4. Minus c2 into cos x minus c3 into sin x equal to 0. This can be taken as equation number 5. Solving these 2 equations 4 and 5. So equation 4 is to be multiplied by sin x plus equation 5 is to be multiplied by cos x. then we get this result. In this, we can take out the common element minus C2. Then we get minus C2 into sin square x plus cos square x equal to 0. This implies minus C2 into 1 equal to 0. Therefore, C2 equal to 0. So using this value in equation number 1, we get C3 into sin x equal to 0. This implies C3 equal to 0. So thus all the constant values are 0. Therefore, the given functions are linearly independent. Next problem, prove that the functions 1, t, t square, t cube, etc., t power n defined in interval minus infinity to plus infinity are linearly independent. So here there are n plus 1 functions. So now we take the linear combination. In the linear combinations, we have n plus 1 constants. So we take the linear combination. Let us C1 plus C2 into t plus C3 into t square plus C4 into t cube plus etc. Cn plus 1 into t power n equal to 0, where C1, C2, C3, etc. Cn plus 1 are constants. Differentiating this with respect to t continuously, we have C2 plus 2C3 into t plus 3 into C4 into t square plus etc. n into Cn plus 1 into t power n minus 1 equal to 0. So here there are n plus 1 functions. Therefore, we can differentiate the linear combination n times. Then if you differentiate the second time, we get 2C3 plus 6C4 into t plus etc. n into n minus 1 into Cn plus 1 into t power n minus 2 equal to 0. This implies if we differentiate this continuously, we get n into n minus 1 into n minus 2 into n minus 3 etc. 3 into 2 into 1 into Cn plus 1 into t power n minus n equal to 0. Here you see this product n into n minus 1 into n minus 2 etc. 3 into 2 into 1. This can be taken as n factorial. So n factorial into Cn plus 1 into t power n minus n, that is t power 0, that is 1. So n factorial into Cn plus 1 equal to 0. This implies Cn plus 1 equal to 0. Using this factorial in the last term, we prove that Cn equal to 0. By proceeding in this manner, we see that Cn minus 1 equal to 0, Cn minus 2 equal to 0, Cn minus 3 equal to 0, etc. C3 equal to 0, C2 equal to 0, C1 equal to 0. Therefore, all constants are 0. Therefore, the given functions are linearly independent. Now we can do the next problem. Define the functions f and g on the interval minus 1 comma plus 1 by f of x equal to 0, g of x equal to x. If x belongs to, that is minus 1 comma 0, that is closed interval minus 1 comma 0. The next f of x equal to sin x and g of x equal to 1 minus x if x belongs to the closed interval 0 comma 1. Prove that f and g are linearly independent on the interval I. Now we write the solution. Let x belongs to the closed interval minus 1 comma 0. In this interval, the functions are defined by f of x equal to 0 and g of x equal to x. So that can be substituted here. So we take the linear combination. Let c1 into f of x plus c2 into g of x equal to 0. In this interval, in this interval minus 1 comma 0, f of x value is 0 and g of x value is x. So here that is to be substituted. That is c1 into f of x value is 0 plus c2 into g of x value is x. So when you simplify this, we get c2 into x equal to 0. This implies c2 equal to 0. This implies C1 and C2 values are 0. Therefore, the given functions are linearly independent on the interval -1, 0. Next, let x belongs to the closed interval 0, 1. In this interval 0, 1, f of x is sin x and g of x is 1 minus x, and that is to be substituted. So let x belongs to this interval 0, 1. This implies let C3 into f of x plus C4 into g of x equal to 0. This implies C3 into sin x plus C4 into 1 minus x equal to 0. This can be taken as equation number 1. So there are two functions. So we can differentiate this linear combination with respect to x one time. So when you differentiate this with respect to x, we get C3 into cos x minus C4 equal to 0. Here C4 into minus 1, that is minus C4 equal to 0. This implies C4 equal to C3 into cos x. Using this result in equation number 1, we get C3 into sin x plus C3 into cos x into 1 minus x equal to 0. We can take it out the common element C3 in this expression. We get C3 into sin x plus 1 minus x equal to 0. This implies C3 equal to 0. So using this result in equation number 1, we get C4 value is also 0. Thus, C3 equal to C4 equal to 0. Therefore, the given functions are linearly independent. Thank you. Right, முடிஞ்சு போச்சு அவ்வளவுதான்.